So in this video we're going to derive Simpson's rule, which is a numerical approximation for an integral that uses quadratic interpolation to reach the answer. So here's the problem then. So we've got some function f of x, and we would like to get an approximation of what the integral of f of x from 0 to this point here is. And we're supposing that we cannot integrate this function analytically. No one can do that. So we can't get the exact answer. So instead we're looking for a numerical approximation of the answer. And this problem arises a lot in applied mathematics. There are loads of things that we would like to integrate that are relevant in physics and engineering where there is no analytic solution to it. No one can get you the perfect answer. No one can actually anti-differentiate the thing we want to integrate to get the perfect answer. So instead, we have to get an approximation to the answer. And with computers, they can do so much calculation that they can actually produce very good approximations to the answer, which are good enough for physics and engineering. Before we begin discussing something called the trapezoid rule, which is simpler than Simpson's rule, and I just want to talk about to set the scene, let me just say that we can say that the integral is going to be from 0 to this point without loss of generality, because even if you wanted the integral from, let's say, this point to this point, all you need to do is translate the whole function along so that it begins, the bit that you're interested in, again, is at 0, and then we've got our original problem of finding the integral from 0 to some point. So translating the function along horizontally does not change the integral that we're trying to find. So without loss of generality, I can just consider this case where we're integrating from 0 to a point. That makes the actual calculation easier. If you try to calculate it for a general point here to here, it just makes it all much more messy. You get the same answer, it's just a clumsier way of doing it. So without loss of generality, we can look at the case from 0 to some point. So just to set the scene for Simpson's rule, I'm going to just quickly discuss a simpler method of numerical approximation for integration, which is called the trapezoid rule. So we are trying to find the integral of our function from 0 to this point, which I'm going to call b just for now. When you are doing either of these rules, either the trapezoid rule or the Simpson's rule, you have to decide how many fragments you're going to split this interval up into. The more fragments you split it up into, the more accurate this approximation is going to be in terms of giving you the answer, but of course the bigger computation it's going to be. So we're going to generate a general rule for however many bits you want to fragment it up into, and we're going to call the number of bits you're segmenting it up into, we're going to call that little n. So what we can now do is split this interval up into that number of segments. So the size of each one of these segments is then going to be little b divided by n, and we'll call that delta x. So our interval from 0 to b then is now going to be split into these little segments, so 0 to delta x to 2 delta x, 2 delta x to 3 delta x, all the way up to b, which will be then little n times delta x. So the trapezoid rule numerical approximation for the integral works as follows. So for each of these little segments, you're going to approximate the area under the curve, and the way you're going to do that is you're going to imagine drawing a straight line from the f value at the first boundary to the f value at the second boundary of the segment. And by the way, I've got some more notation on my picture here. So for each of these points, we have given the value the function takes at that point. We're just calling that f subscript the value of the point you've got to. So for 0, where you've gone forward 0 delta x's, we're calling the value of f there f subscript 0. For this point here, delta x, where you've gone forward 1 delta x, we're calling the value of the function there f subscript 1. For 2 delta x, it's f subscript 2, etc., all the way to n delta x, where it'll be f subscript n. I hope that's clear. So For this first segment from 0 to delta x then, you're going to draw a straight line from this point here, which is 0, f0, to this point here, which is delta x, f1, and you're then going to approximate the area as this trapezium here. So it's made up of this triangle here, and then this rectangle here. Now what's the area of that? You could find the area of this rectangle and add it to the area of that triangle, but be cleverer. Think like if you took the average of f1 and f0, you'll get halfway up that triangle, and then if you imagine slicing off the top of the triangle, you can put that in that space that's left here, and then it will just be a rectangle of height, the average of f0 and f1, and then width delta x. So here's the average of f0 plus f1 and f1, and then we're timesing it by the width of that rectangle delta x, and that will give the area of this entire red trapezium. Continuing on, the area for then the trapezium for the second one, again you draw a straight line from this point to this point, and then you'd want the area of that trapezium. That's going to be the average of f1 and f2 times delta x, and so on. So you'll go finally to the final trapezium, which will be from n minus 1 times delta x, fn minus 1, to n delta x, with the corresponding f value of fn, and that trapezium will have value the average of fn minus 1 and fn times delta x. And then you can, this total sum is then the approximation for the integral of the function from 0 to n delta x, and I might just write that down. So the integral of f of x from 0 to n delta x is approximately going to be equal to this thing here, and we can make this look nicer, so we can factor out the delta x over 2, and then we're going to get f0 plus, because this term and this term have f1, you'll end up with 2f1, then you'll end up with 2 f2s, because f2 will be in this one and it will be in the next one along, and so on. You'll end up with 2 fn minus 1s, because it's in this final one, but it's also in the one preceding it, and then just 1 fn, because there's only one that contains it. So the two boundary ones will only appear once, but all the ones in between will appear twice. So this formula then gives you an approximation for that integral. And the bigger you make n, the better this approximation will be, because you can imagine that the number of intervals, the number of segments that you're dividing this into is going to get smaller and smaller, so you're going to have a finer and finer approximation that's going to be closer and closer to the true thing. But the bigger this formula is going to become, the bigger n is. And this formula holds true even for the case where we haven't got the integral beginning at 0 and going somewhere. So if we consider trying to approximate this integral of f of x from a to b, all we need to do is divide this up into however many segments we're going to do for our approximation, so little n, so we'll just make delta x equal to the length of this line, which is just b minus a, and then divide it by the number of segments we're going to divide it into, so little n there. Then these f's, we can still use these same subscripts. The way it's just going to work is that f0 is going to be f at a, and then f1 will be f at a plus 1 times delta x, f2 will be f at a plus 2 times delta x, etc. So the number at the subscript, it refers to how many delta x's you've gone forward. So fi is just going to be equal to f at a plus I delta x. So that's the way this formula is going to continue working in this case. So that was the trapezoid rule for numerical integration. We're now going to look at Simpson's rule for numerical integration, which is another way of approximating an integral. We are going to derive Simpson's rule. What we are not going to discuss in this video is which one is better, the trapezoid rule or Simpson's rule. Meaning, if you have a function and you want to approximate the integral from 0 to this point, and you are splitting the interval into a certain number, little n, of segments, which of these formulas the formula for the trapezoid rule or the formula for the Simpson's rule, which one is going to be better? That is not a simple question to answer. It's a brilliant question, but it's not a simple question to answer. And it depends which function you're dealing with is the reality. Some functions will be better approximated by the trapezoid rule, others will be better approximated by the Simpson's rule, others will be better approximated by other further methods of numerical integration that we haven't discussed in this video. We're not going to say any more about that now, we're just going to derive the result for Simpson's approximation for an integral. So we're going to use all the same notation that we've previously used. This exact same picture holds. We're trying to work out the integral from 0 to b, and we're going to divide this interval up into little n pieces, and we'll call the size of the interval as delta x, which is just going to be b divided by n. This time, n is going to need to be even. It can't be odd. And the reason for that is the way we're going to approximate this integral is we're going to produce a quadratic approximation or a quadratic interpolation for going through 3 points at a time, and then we're going to integrate underneath that quadratic curve to approximate the area underneath our actual function. Therefore, it's going to work using 2 segments at once. So we will get these 2 segments as a single answer, and then we'll move on and we'll get the next 2 segments, because each time you do one of these approximations, you're going to be working with 3 points that you're going to fit the quadratic curve using Lagrange interpolation, or in fact we don't even need to call it Lagrange interpolation, it's just quadratic interpolation. So you're going to fit a quadratic through 3 points, work out the area underneath that quadratic, use that as your approximation, and then you'll move on, and the next 3 points will be correspond to the next 2 segments, etc. So you have to make sure that the number of segments you've got here is going to be even, so n is going to need to be even in this case. So let's do this then. So I've drawn down here, this is the same picture as up here, so this is our function f, and now we're just zooming in on this first pair of 2 segments, and we're going to do this calculation. We're going to quadratically interpolate the function using these 3 points, and then we're going to integrate underneath it to get the integral from here to here, which will serve as our approximation for the integral of our actual function from here to here. And then we will get a formula for this, and then we'll see how that formula will then be applied to all the other pairs of segments, and therefore will arrive overall at Simpson's rule. So the first thing then to do is actually find the formula for the quadratic interpolation through these 3 points. So this is the quadratic interpolation formula, which is just the Lagrange interpolation formula for 3 points, where you end up with a quadratic. So the Lagrange interpolation formula tells you how to do it for any number of points, and the more points you're insisting on, the higher degree the polynomial will end up. In fact, the degree of the polynomial will be the number of points minus 1. So in this case, we've got 3 points, so minus 1 is 2, so we can get a degree 2 polynomial that will go through all 3 points. And this is the formula for that polynomial. So this looks horrific, but it's actually incredibly simple. So again, look at this. If you're not familiar with interpolation, and I hope the viewers are all familiar with why this works, but I am just going to explain it in case there is anyone watching who doesn't understand this. So we want to produce a quadratic function, a quadratic polynomial that will go through each of these 3 points. How can we do that? Well, so we want it to equal f0 when you put in x is equal to 0 here. But we don't want it to equal f0 when you put in delta x or 2 delta x. Instead, for delta x, we want it to equal f1, and for 2 delta x, we want it to equal f2. So we start by putting f0, and then we multiply this by x minus delta x and x minus 2 delta x. The reason we do this is because this ensures that at delta x and 2 delta x, this will go to 0, this term of our polynomial will go to 0, and therefore you won't get it equaling f0. Then we think, but we actually want it to equal f0 when we put in 0, so if we put in 0 here, at the moment we'd get f0 times minus delta x times minus 2 delta x, which is what you get when you put in 0 for x here. That's no use at all. So what we then do is divide through by those things. So we put divided by minus delta x and divided by minus 2 delta x. And this term, if you put in 0, will give you f0. Brilliant. And when you put in these two things, you will get 0. Then we're going to do exactly the same thing for these 2 points now. So for f1 is the answer that we want at delta x. We don't want that answer at 0 and 2 delta x. So we put in f1 times x minus 0 times x minus 2 delta x. So these things ensure that when you put 0 into this term, you get 0. And when you put in 2 delta x to this term, you get 0. Brilliant. So that doesn't disturb the answer being right at 0. At the moment, if we just had this term, this would be perfect at 0. It would give the correct answer at 0, but it's not going to give the correct answer at these 2 points. So that's why these two terms have to come in. At the moment, that gives 0 at these 2 points. It gives the correct one there, but it then goes through 0 and 0. That's what we've got if we just use that as our quadratic interpolation. It's not the correct answer. But now we're going to add on these terms to make it go through these 2 points. So this means that it's not going to disturb our correct answer for 0 that we've got from this one. Indeed, this is just going to go to 0, so it's not going to disturb that. It's also not going to disturb the correct answer that this one is going to give for 2 delta x. The final thing we have to do again is divide through by this to make sure that it actually gives the correct answer at delta x, because if we didn't have this, then we'd put in delta x here and we'd get delta x times negative delta x. Which would then give f1 times negative delta x squared, so it wouldn't give the correct answer. We want the answer to be f1. So we therefore have to divide through by these two things, which then makes this equal to, this bit equal to 1 times f1. So this and this together, they go through this point and this point. They don't go through this point. At the moment, they're going through 0 at 2 delta x. So then finally, we add on this term. The reason it has to have this bit and this bit in is so that it doesn't disturb the correct answers that we've got at these 2 points, and then it needs to be divided through here by this so that it gives the correct answer of f2 at 2 delta x. So that's the reason this formula works. Very clever. So that is the quadratic interpolation for our function over this region. Now, I've drawn in red here. This is supposed to represent the graph of this function. So remember, even though it in this case looks very similar to the actual function, it's not actually equal to the function. It's an approximation to the function that might be very nicely curve-fitted to it, as it is in this case. So we want to integrate this. In order to integrate this, let's firstly do some algebraic manipulations so that we can get it in a form that's actually going to be easy to integrate. So this is where it gets confusing. We're very liable to make a silly mistake at this point, especially because delta x looks so similar to x. Remember, delta x is a constant that has already been set. It's just you had that interval over which you're integrating. You decided on how many bits you were going to split it up into, little n, which had to be even in this case. And then delta x is just the length of the interval divided by little n. So it's not a variable. Do not get confused by that. It's a constant. But annoyingly, it is going to look very like a variable. But we must not be daunted by that, and we must not be confused by that. We could have called delta x equal to little h. That would have been another acceptable way of doing this. In fact, it probably would have been a tidy way, but I'm not going to change now. So we're going to carry on, but we're going to be very careful. So let's start with this one here. So we've pulled out the f0 and we pulled out the 2 delta x squared from the bottom. So the minuses have cancelled. So that's where this bit comes from. We then multiplied these brackets out. So we get x squared, which is this times this. And then we're going to get minus 2 delta x, and we're also going to get a minus delta x. So we overall get minus 3 delta x. And remember, this is nothing to do with this. And then finally, we get this times this, which is just plus 2 delta x squared. That's fine. This one then, again, we've pulled out the f1 and we've pulled out the delta x times the negative delta x. So we get minus f1 over delta x squared. And then multiplying these two out, this, remember, is just x. So this is going to be x squared minus 2 delta x. And again, this looks really confusing, but it's not. That you could have just replaced with an h. It's just a constant. Then finally this one, so again pull out the f2 and the 2 delta x from the denominator, and then you've got x times this, so we get x squared minus delta x, x. So now what we're going to do is rearrange this so that all the quadratic terms are together, all the x to the power of 1 terms are together, and all the constant terms are together. So beginning with x squared, these three. So we get f0 over 2 delta x, then we get this bit, which is minus f1 over delta x squared, and then we get this bit, so plus f2 over 2 delta x squared. All of that, that's the coefficient of x squared. So that's just that term, and that term put together, and then we've factored out the x squared. Then we want to collect the x terms together, so these three, and again we'll factor out the x, so we've got the x here. So term number 1, this is a bit more confusing because things are going to cancel, so we've got a negative sign, annoyingly. So we're going to get minus 3 times f0 over the 2's from there, and then the delta x cancels with one of the delta x's from here, so it's just over delta x now rather than over delta x squared. Then this term here, the delta x is going to cancel again, so we just get plus this time because the minus is cancelled with the minus, so plus 2 times f1 over delta x, and then this final one, so again it's going to be minus, delta x cancels, so it's just minus f2 over 2 delta x times x. And then there's only one constant term, so neither of these have a constant term, so it's just this one, so 2 delta x squared cancels completely and you just get plus f0. So this is now in perfect form to integrate, and remember what we've still got here, this is just the final formula for that quadratic interpolation that goes through those 3 points. So we want to integrate this now, and I've inserted the integration symbols here. So firstly, let me just remind you that we're going to integrate from 0 to 2 delta x, because we've got our quadratic interpolation in red, and we want to integrate from 0 to 2 delta x so that we can get the area underneath the curve of the quadratic interpolation and use that as an approximation for the area underneath our real function f from 0 to 2 delta x. So we've got the integral of this first thing, this quadratic term from 0 to 2 delta x dx. We've got this integral here of the power 1 term, so from 0 to 2 delta x, and then the constant term here from 0 to 2 delta x. And remember, these are just constants, so they are easy in integration. They can be pulled out the front. So we're just integrating x squared, x, and a constant term, so this is not complicated. So I don't want to have to write all of this mess out again, so let's just think about this. This will come out the front, and we're integrating x squared. X squared integrated is x cubed over 3, and we want to evaluate that between 0 and 2 delta x. This one, again, imagine pulling out the front, we're just integrating x, which is going to be x squared over 2, and we're going to evaluate it from 0 to 2 delta x. This one, put the f0 out the front, and then you're just integrating 1, which is going to be x, and you're going to evaluate it again from 0 to 2 delta x. So this one here is just going to be put in 2 delta x cubed over 3 and then subtract off what 0 inputted in here is, but 0 cubed is just going to be 0, so you're subtracting off 0. So the answer to this is this, 2 delta x cubed over 3 multiplied by this great big constant out the front. This one then, again, same thing's going to happen, just put 2 delta x into this, you get 2 delta x squared over 2, and then you're subtracting off 0 squared over 2, which is just 0, so this is equal to this, and then you need to remember to multiply it by all of this. This one, evaluated between 0 and 2, put 2 delta x in here, you get 2 delta x, subtract off 0 in here, so you're subtracting off 0, so this is just equal to this, and again you need to multiply it by f0. So now this is looking very hopeful. We're going to multiply this by this and add it to this, multiply by this and add it to this, multiplied by this. Let's do that. So here we go, let's talk through this. So 2 delta x cubed over 3 is 8 delta x cubed over 3. 2 delta x all squared over 2, that's equal to 4 times delta x squared over 2, which is the same as 2 delta x squared. And then, of course, 2 delta x is just going to remain 2 delta x. So let's do this. Let's multiply this by all of this. So this one times this one. So we're going to get f0. The 8 is going to cancel with the 2 to give us 4, so we've got 4 f0. Then delta x cubed is going to cancel with the delta x squared to just leave delta x. And then you're still going to have this 3 here, so over 3. So that's where that bit comes from. This one then now. So we're going to get the f1, so we're going to get minus f1. We're going to have the 8 and the 3, so there's the 8 and the 3, and then the delta x cubed is going to cancel with that delta x squared to just give delta x. So that's where that bit comes from. This bit here, so the 8 again is going to cancel with the 2 to just give 4. Again, you've got the f2. The delta x cubed cancels with the delta x squared to give delta x, and you keep that 3, so over 3. This bit, so we're going to multiply this by this. So the 2 and the delta x squared are going to cancel, so this 2's gone, this delta x is gone, so you'll get delta x, and then you'll have minus 3f0 left, so minus 3f0 delta x here. This bit, so you're going to keep the f1, so that's there. Now we've got the 2 times the 2, so that's 4. The delta x squared cancels with the delta x, so you get plus 4 f1 delta x, so that's where that bit goes. This bit here now, so the 2 delta x squared will cancel with the 2 delta x, we're just going to get delta x, so we'll get minus f2 times delta x. And then finally we've got f0 times this thing, which is just 2 f0 delta x. And this is the point where I pray I haven't made a mistake, so let's look at this further. So let's pull out the delta x, and let's actually also pull out an over 3. So let's pull out delta x over 3. You'll see why this is an excellent thing to do. You know, as we saw in the trapezoid rule, we had delta x over 2 out the front. In Simpson's rule, we're going to have delta x over 3 out the front. So we'll do this. So pulling out delta x over 3, here we get 4f0, here we get 8f1 or minus 8f1 really. Here we get plus 4f2. Here we're going to have to multiply by 3 to compensate for our pulling out of the third. So it's going to give us minus 9f0, so that bit comes here. This one we're going to again have to multiply by 3, so it's going to give us 12 times f1. This one again multiplied by 3, so we'll get minus 3f2. And this one finally again multiplied by 3, so we'll get plus 6f0 inside here. So all of this multiplied by delta x over 3. And now let's just work this out. So this is the overall answer we get. So let's just talk through this quickly. So f0s, we've got this one, plus this one makes 10, and then subtract off 9, so we've got 1. f1s, we've got this one, and then this one, so 12 minus 8, we've got 4. f2s, we've got this one and this one, so we've got 4 minus 3, which is 1. So it overall gives this beautiful expression, delta x over 3 times f0 plus 4f1 plus f2. And remember what this means. That is the integral underneath our quadratic interpolation. So this then is the approximation for the integral of our function from 0 to 2 delta x. So coming back up to our original problem then, so we're trying to get this approximation for the integral of our function f of x from 0 to this point b. And what we have done so far is we've divided our interval from 0 to b up into little n pieces where little n is even, and we have taken the first 2 of these pieces, we've produced a quadratic interpolation approximation for the function, and then we've integrated that to get an approximation for the area underneath our original f of x, which is the which is the area underneath the curve of the quadratic interpolation. And we know that that value is given by this here, delta x over 3 times f0 plus 4f1 plus f2. What we could now do is move forward to the next 2 little segments, so from 2 delta x to 3 delta x, and from 3 delta x to 4 delta x, which isn't drawn on here, but those next 2 segments, and we could do exactly the same thing. We could build a quadratic interpolation for that portion of the curve that will go through this point, 2 delta x, f of 2, 3 delta x, f of 3, and 4 delta x, f of 4. Then we can integrate that and use that value as the approximation to the integral of our function f over that interval from 2 delta x to 4 delta x. And the formula for that is going to be exactly the same. There was nothing special about this, so it's going to be of this form, so delta x over 3, and then f2 will take the place of f0, f3 is the one in the middle, so we'll take the place of f1, so plus 4f3, and then f4 will take the place of f2. Now you might say, but there was something special about this. This was centered or started at 0, and 0 made all the algebra and the integration simpler. Remember, the algebra was made simpler by the fact that in the interpolation formula we had several of the terms were just x minus 0 rather than x minus something. And the calculus was made simple by the fact that we were integrating from 0 to something, and then that lower part meant that when we actually came to evaluate the integral, we were just subtracting off 0. So it made it simpler. But you could just imagine if you were trying to calculate for, let's say, this bit, so from 2 delta x to 4 delta x, you can just imagine horizontally translating that to here, and then doing all the equivalent algebra and calculus in this position of the coordinate system, and then you'd get this as the overall answer. So this is correct. The algebra is messier and the calculus is messier if you try and actually do it by putting in 2 delta x and 4 delta x. You can make the algebra simpler by just imagining translating it back to the position so that 2 delta x is now 0 and 4 delta x is now equivalent to 2 delta x. But you'll overall get this answer, and I hope I've convinced you that you will get this answer. So we can do this for each of the pairs of segments in our interval from 0 to b, and this is why it was so important that the number of the segments was even so that they're in pairs. And we can add them all together, and that will then be Simpson's rule for the approximation of the integral of f of x. So we'll have this one plus this one, and then it will go on. So we'll have delta x over 3 times f of 4 plus 4 f of 5 plus f of 6, and on all the way up until the final one, which will be delta x over 3 times f of n minus 1 plus 4 f of n minus 1, sorry, n minus 2 here, f of n minus 2 plus 4 f of n minus 1 plus then finally f of n. So overall, combining these terms together then to get the final form of Simpson's rule, so we have that the integral from 0 to n delta x of f of x dx is going to approximately be equal to, and then we've got delta x over 3 out the front, that's obvious, and then we're combining all of these together, so the first and the last term are only going to appear once, so we'll have f0 and fn right at the end, and they'll just have 1s in front of them. Then the odd terms will all have 4 in front of them, so we've got plus 4 f1. The even terms that are in the middle, they're going to have 2 in front of them because each of them are going to appear in 2 of these statements, or 2 of these terms that we're combining. So f2 is here and f2 is here, so you get plus 2f2. Then you've got the plus 4f3. For f4 finally, it will appear here, and then it will also appear in the next one, so you've got plus 2f4, then you'll have plus 4f5 plus 2f6, and it will alternate in this way, so you'll have 4 times the odd terms, and then 2 times the even terms, and then the 2 terms right at the end are the only ones with 1 in front of them. So that's it in its final form. This is Simpson's rule for numerical integration or numerical approximation of integration. Let's just compare it to the trapezoid rule that we saw earlier. So here is the trapezoid rule with the delta x over 2 out the front, and then we have f0 and fn with 1 in front of them, and then all the other terms in the middle with 2 in front of them. And here we have Simpson's rule where we have delta x over 3 out the front, f0 and fn have 1 in front of them, and then the terms inside, the odd terms have 4 in front of them, and the even terms have 2 in front of them. So very different overall results. So the big question then, which we talked about earlier, is if we have a given n, i.e. we have a set number that we're going to divide our interval up into, and n is going to have to be even for us to be able to use Simpson's rule, we can ask which of these two is better. And the answer is often this one, but not always. And we won't say any more about that in this video. So we'll end there. We've derived this result, shown where it comes from. I hope you've understood that derivation, and I hope you overall enjoyed the video.